In this video, we're going to talk about minors and planarity. Now, I hinted at this at the end of the last lecture that you can start to characterize what kind of graphs are planar in terms of what kinds of minors they have. And we're going to sort of back into that problem. That is, we're going to look at some simple examples and we're going to work through some other cases of graphs where it's not planar, and we're going to see how their non-planarity is related to the kinds of minors or topological minors they might have. And this is going to give us our intuition and some of our basic tools for proving what I think is perhaps the most important theorem or theorems about planar graphs. And that's going to be a characterization of planar graphs that's purely combinatorial, which means even though planarity is a statement about topology, it's about the existence of certain continuous maps between topological spaces, it could be understood in a purely combinatorial way. We've gotten hints of this before. If you think back, we saw, for instance, that we could characterize the faces of three connected planar graphs just in terms of certain kinds of cycles, non-separating induced cycles, don't forget those. For three connected planar graphs, those are going to bound the faces in every embedding. So it makes sense for us to try to maybe characterize all of planar graph theory in terms of structures that are maybe not there, and those structures are going to be minors or topological minors. So to jump into it, let's look at this example. This is a classic fun graph. It shows up all the time. It's fun because it's a little counterintuitive. It turns into a counterexample for a bunch of natural conjectures you might make about different graph properties as you're exploring small graphs. It's sometimes called the Petersen graph. It's always called the Petersen graph, but sometimes it might be called a Petersen graph because there are several. But maybe this is the most popular one. And so it looks like, what does it look like? It's like a star inside a pentagon where the star is connected out to the pentagon. And I've drawn it with a bunch of crossings here. It's not too hard to see. You could do it with fewer crossings. I don't know how many fewer. What do you think? Think about it. Can you get away with no crossings? Like, is this graph planar? And, well, I'm going to let you think about it. But before we get there, it looks a little bit like, it may remind you of another graph. It may remind you a little bit like K5. It kind of looks like, I don't know, somehow we could treat this like it was K5. You know, if I just, I don't know, can I contract it to K5? I think I can. And we'll see what that means. But would that help me? So you may have tried to draw K5 before. In fact, I don't even remember. Perhaps we even looked at this question before. K5, is it planar or not? And if it's not, does that help us? Does that tell us anything about the Petersen graph? That's kind of going to be the question we're going to ask. All right. So it is, in fact, true that K5 is not planar. And there are a bunch of simple proofs of this fact. Here is one of my favorites. So I will start as follows. So I'm just going to observe that K5 has 5 vertices and 10 edges. Now, suppose, for contradiction, that it is planar. If it's planar, well, we know something about planar graphs. We know that there's some maximum number of edges that can appear in any planar graph. That is, we know from Euler's formula, I'll just write Euler, it implies that the number of edges is less than or equal to 3 times the number of vertices minus 6. So if we plug this in, is 10 less than or equal to 3 times 5 minus 6, which is equal to 9? No, it's not. So there's our contradiction. That's the whole proof. Done. Just defies our basic upper bound on the number of edges in a graph for any planar graph that we derived from Euler's formula. So that is a real quick proof that K5 is not planar. You could also prove it perhaps by thinking about an embedding and showing that if you remove one vertex, you end up with an outer planar embedding of K4. That's another nice little proof. And I'm sure there's a couple other ways of thinking about this. All right. So what does that give us? Well, I claim that now if G contains a subdivision of K5, then G is also not planar. And take notice of what we've just done here. We had an example of a specific graph that was not planar, and we're going to use it now as leverage to prove other graphs are not planar. In this case, it's just if it has a subdivision of that non-planar graph, then that graph is also not planar. And I could just prove this lemma, but it seems like we might want to do it even slightly more generally. In this case, I claim the following. We could just prove this theorem. If H is non-planar, non-planar just means not planar, and H is a topological minor of G. And if you didn't notice, when we say it contains a subdivision of another graph, that's the same as saying, in this case, K5 is a topological minor of G. So more generally, if I have a non-planar graph that's a topological minor of my other graph, G, then G is also not planar. And this proof is relatively straightforward. But before I go on, let me just give you a second to think. Do you see, hopefully, how this lemma, which will now be a corollary to this theorem, how this follows directly from this theorem? It's just a special case, given that we know K5 is non-planar. So take H equals K5. We know K5 is not planar, so it plays that role. But it didn't matter if we had any other non-planar graph, and we found it as a subdivision in G, we would know that G was not planar. All right, so here's how we prove it. All right, so what do we know? Since H is a topological minor of G, that implies there's some subgraph, G prime, subgraph of G, and that subgraph is homeomorphic to H. So let's write that homeomorphism. Let's give it a name. So there's some F, which maps the geometric realization of H homeomorphically to the geometric realization of this subgraph. And that follows from the fact that this G prime is going to be a subdivision of H, and subdivisions are homeomorphic. Suppose for contradiction that G is planar. If we could prove that H must also be planar, then we would have a contradiction because we assumed, that's the hypothesis of this theorem, is that H is not planar. And so that's the pattern we're going to go with. We're going to try to take this supposition that G is planar, and we're going to try to construct a planar embedding of H. And to prove a graph is planar, perhaps the most direct way to prove that a graph is planar is to just give an embedding. That is, to somehow write down exactly what the embedding should be. And that's not always easy to do, but in this case we've got a head start because we're going to assume we have an embedding of G. So let's let phi be that embedding of G. Oh, sorry, I should be careful. An embedding of G prime. So G prime has to also be planar because it's a subgraph of G. And we just assumed that G was planar. So this is the embedding. So let phi here be the embedding. I drew my little hook arrow here to imply that it's injective, and therefore, as a map between topological spaces, it's injective, and therefore, this is what it means to be an embedding of a graph. And now we're almost there, because we now can take that embedding and use it to embed H just by kind of combining it with the homeomorphism F, because phi composed with F is a continuous map from the geometric realization of H into the plane. That's just composition. And homeomorphisms are injective, so the composition is injective. And so this is an embedding. Oops, an embedding. But it's embedding of H. Right, that implies that H is planar, which is exactly the contradiction we wanted. Right, so we conclude that G is not planar. Right, so we conclude that whatever we supposed here was in fact false, because we derived this contradiction that H is both planar and non-planar at the same time, which is impossible. Okay, so this gives us also a good chance to see how we use a homeomorphism to relate one embedding to another, to actually construct an embedding of one graph from the embedding of another graph. All right. But what does this tell us about the Petersen graph? Let's call it P. I claim the following, and we're gonna see a proof of this in a second. It will follow from the theorem we just proved. But I claim that it's non-planar. And even though I say it, we still have to ask, like, why? Why can I be sure? If I talk about a graph being non-planar, that's saying that it doesn't have any embedding in the plane. Like, there doesn't exist one. But to say that it doesn't exist doesn't mean that I just tried really hard and couldn't find one. It says that no one could find one. It's also true that this K5 is not a topological minor of P. It's not, I put it is, it's not one. So there's no K5 topological minor. And we've already discussed why in different contexts. You see the degrees of these vertices. Every vertex in P has degree 3. So it can't have a topological minor with vertices of degree 4. So this is not the case. So the theorem we just proved is not going to help us. So that might be frustrating. You say, man, we knew how to find one graph that was not planar. And we knew that if we could find it as a subdivision in another graph, we could show that the other graph was not planar. But it's just not going to work here. So I'll just put this real quick. The proof here is just that the min degree is 3 in P, 4 in K5. Not possible. However, you know, we had this intuition that I had this intuition. I hope you did too. That it looks a little bit like the usual drawing of K5. In fact, if we just contract these edges, connecting these two, we just treat these as now combined vertices, the result, in fact, is K5. So there's a contraction here. So the Petersen graph just contracts to K5, which means that K5 is a minor of P. And, but we don't know what to do with that. Oh, I don't know why I put the 5 over here. This should be a M, sorry. Does this help? Not yet. It would seem that if we didn't require it to be a topological minor and it was just any old minor, then this would be a really easy way for us to quickly see that it's not planar. In this case, there's another graph, another very simple graph that is not planar, that is a topological minor of this. And that graph is K33. So K33 is a topological minor of G, and also it's not planar. We'll prove that in a second. But I just want you to take a second and think now, first of all, is this really true? It's not the easiest thing to find this. I'm going to try to do it. Let's see. Let's see how I do. I'm going to take this guy. I'll take green here. 1, 2, 3, like that. And red will be maybe the other set. How about this one, and this one? And now I got to find my edges. And this is going to be such a mess that you won't be able to tell what I did, but I'm going to give it a try anyway. So I need edges from this green vertex to each of the red ones. So I'm going to take this one here, this one, and this one. Oh, it already had the edges. Beautiful. That was easy. Now I need edges from this green vertex to each of the red ones. Well, maybe it won't have edges, but I at least need paths. Let's see what I can do. How about this one? Does it work? Did I mess it up? Oh no. Let's see. How do I get over here? How about I go up this way and over here to that one, and then I come around. Nope, didn't want to do that. Well, maybe I should go around this way. Am I stuck? One to green to red. Well, I have no idea. I think I messed up. I think what I just did was I just really gave you a really convincing proof that it's not obvious. You're gonna have to fix this for me. You're gonna have to find somewhere in there. I'm pretty sure. I really firmly believe there's a K33 topological minor. But I'll leave it to you to find it. So if you do find it, and you also prove that K33 is not planar, well, this previous theorem will say that, okay, then the Petersen graph is not planar. So let's do that other step first. That K33 is not planar. First observation to make. K33 is 3 connected. If you remove any 2 vertices, you're going to end up with either K13 or K22, depending on if you took them both from the same side or from different sides. All right, so K13 and K22 are connected. These go by some other names you may recall. For instance, we called K13, we called that the star on 3, this was S3, and this K22 is just C4. So there are 9 non-separating induced cycles in K33. So recall a non-separating induced cycle. It's a cycle that if I remove it, the graph is still connected, and it's induced, which means that the only edges among the vertices in that cycle are exactly the edges in the cycle. So I can get one of these non-separating induced cycles just by picking out any 2 vertices from one part of the partition and any 2 vertices of the other part, because the result will be a K22, it'll be a C4, the induced subgraph is a cycle of length 4. And there's not going to be any cycles of length 3 or 5 because it's bipartite and there are no odd cycles in a bipartite graph. And there won't be a cycle of length 6 because if I took all 6 vertices, I'm going to end up with some extra edges, so it won't be an induced cycle. Okay, so I get one non-separating induced cycle for each K22, again, this is a C4 subgraph. So now that means I know some things. If I suppose, for contradiction, that this graph really is planar, so suppose that K33 is planar. And since it's 3 connected, these non-separating induced cycles are the faces. So now I know the faces, there are 9 of them. And I can apply Euler's formula. I know the number of vertices, edges, and faces. It should be the case that n minus m plus f is equal to 2. However, we have 6 vertices minus those 9 edges plus those 9 faces is not equal to 2. And since this should be true for all planar graphs, we have a contradiction. It means is that this graph was not planar, and therefore K33 not planar, done. All right, so knowing that K33 is not planar, if you did your work and you found that K33 topological minor inside the Petersen graph, that would imply that the Petersen graph is not planar. And it means now that we have two different examples of non-planar graphs. And if we apply our theorem, we see that, okay, any graph G that has K5 or K33 as a topological minor itself cannot be planar. So we have a quick criterion, hopefully pretty quick criterion, that allows us to check if a graph is not planar. If we can find this structure, then we know it's not planar. Amazing, amazing fact. Beautiful, incredible theorem, and we're going to prove it, is that in fact the opposite holds. This is a theorem of Kuratowski that if it's not planar, then it has one of these subgraphs. That means that these two, K5 and K33, are the canonical examples of non-planar graphs, and they're the only ones you need. If you have a graph that's not planar, you will find one of these two subgraphs. A subdivision of one of these two graphs. Certainly if it's a subgraph, it's a subdivision. And so that's an amazing, beautiful fact. It says now this property of being planar can just be completely characterized in terms of forbidden topological minors. But I claim there might be some sneaking suspicion that we should have just been able to use minors and not required topological minors. That maybe we could have found that the Petersen graph was not planar just because it had the K5 minor and not just the topological minor K33. So right now, I've hopefully just set it up so that you suspect this might be true, that we could replace that property of being a topological minor with being a minor, and that this will still hold, that graphs are planar if and only if they don't have K5 or K33 as minors. And that would give us a lot more freedom in searching for an obstruction to being planar, to find a minor rather than a topological minor. And it's true, we can do this. So good news, that's Wagner's theorem. Both of these theorems were proven in the 1930s. 1930 for Kuratowski, 1937 for Wagner. And we'll prove both of them, and we'll prove both of them together. In some sense, you might have expected that we should have, if we were going to prove this, we might as well have done it just when we were in the section on topology. And now that we've kind of moved on to simplicial complexes, simplicial maps and contractions, and minors more generally, we're going to do them both at the same time. We're going to prove them equivalent and do that. But first, we're going to have a couple videos where we cover some other basic tools for analyzing minors of graphs, certain facts about certain minors that exist or certain kinds of contractions that exist in graphs. And that will help us to prove both Kuratowski's theorem and Wagner's theorem, which gives a nice, complete characterization of planar graphs. And we'll do that in just the next 2 or 3 videos. So stay tuned.